Hello. Starting today, we will begin our deep learning class. The reason I named it Deep Learning and Design is because our class will cover the basics of deep learning. We will cover the basics and introduce representative models, but from an application perspective, I named it this way because we mainly focus on how to use deep learning in engineering design. Today, let us start with Chapter 1, Introduction. And I have listed the references used in this course. You can download our lecture slides and practice codes by visiting this site. And our students worked hard on the practice code. And the lecture sources, well, I didn't create everything from scratch. There are so many great open source lectures available, so I based my materials on those. If you are new to deep learning, there are some essential courses you should learn. For example, you can look at these 5 courses listed above. So, Professor Andrew Ng, a very famous professor in deep learning, created a machine learning class. Although it is an English lecture, there are many Korean versions available. It is so famous that you can easily find it, and there is a course at Stanford called CS231N, and you can learn about the latest deep learning technologies in more depth. These are also all open to the public on YouTube. And well, if you want to learn more about things like deep generative models, there are actually so many lectures available on the internet. So if you have even a little bit of interest, you can find and take all of them. And the code is also very well organized. However, for those just starting out, Korean lectures will be more comfortable than English ones. Deep Learning for Everyone by Professor Sang Kim is very famous. So take this course first. It starts with the very basics of TensorFlow. However, as TensorFlow moved from version 1.0 to 2.0, the coding method changed a bit. So Deep Learning Season 2 introduces these updated methodologies. So even if you take this class, well, you don't have to take both. But for example, if you're taking the second one or the latest one, I think it's good to take this as a basic course. Yes, the content of this class is largely divided into chapters 1, 2, and 3. Today we will cover what deep learning is and how it can be applied to engineering design. After that, we will learn about supervised learning and unsupervised learning. I think many of you are now quite familiar with deep learning, or at least the term itself. However, terms like artificial intelligence, machine learning, and deep learning are often used interchangeably. So I think we need to take a look at the structure to understand what each of these actually means. You can think of AI or artificial intelligence as research into creating machines or systems that think and act like humans. This research has been going on for a very long time. Deep learning that is commonly talked about and in the spotlight these days, that is not the only AI. You should think of deep learning itself as just one part, one field of AI. So whether it is data-driven or rule-based, all technologies that make machines think and act like humans are called AI. There was a time when even simple if statements were considered AI. After that, machine learning began to develop. Machine learning is a field of artificial intelligence that enables machines to learn, right? So you can think of it as a research field that belongs to artificial intelligence. The difference is that it is achieved through learning. That is the key feature. While it can be done through rules, machine learning is artificial intelligence that requires data through learning. So saying this artificial intelligence technology has advanced significantly. For the basic summary, there is regression. You have all probably dealt with regression analysis at least once. You can think of regression analysis as a method of machine learning as well. Any method that involves fitting based on data can be called machine learning. So, what is deep learning? Deep learning is machine learning with a deep neural network structure. So it is also a field of machine learning. It is machine learning that has a deep neural network structure. So these deep neural network structures, we call these neural network structures neural networks. So artificial neural networks, or abbreviated as NN for neural networks. We will cover this in class as well, but ultimately, this neural network is a method of machine learning. Now, this neural network from machine learning, as you will learn later, has only one layer between the input and the output. This is what a neural network looks like, for example. The moment there are multiple hidden layers in the middle, the moment there are many of them, it becomes deeper. That is why we say it gets deeper. So it becomes a deep neural network, or DNN. That is this deep neural network structure. So to explain it very simply, there is something called a neural network in machine learning, and when the hidden layers of that neural network are stacked and become deep, that became deep learning. So that is the most basic concept, and after that, various architectures began to develop. So you can think of deep learning as a part of machine learning. Then, if you ask why deep learning didn't exist or wasn't this popular in the past, research on deep learning had been ongoing, but it was blocked for certain reasons. In other words, its usability was very low. There are 3 reasons for this. First, there was a lack of data in the past. But nowadays, with the development of the internet and IoT technology, it has become very easy to obtain data in real time, and there is a massive amount of big data available.
So the point is that data is easy to obtain.
Second, technology for graphics processing units, which allow for distributed and parallel processing, has advanced so much that the massive computational requirements of deep learning, which were once a hurdle, have finally begun to be resolved. And third, deep learning architectures. The technologies required for these deep learning architectures have advanced significantly. In particular, there were a few bottlenecks, reasons why it was difficult to train these deep neural networks, but those key reasons were resolved. I will introduce those as well later on. So, with these 3 conditions met, deep learning is gaining a lot of attention these days, and it is showing some very powerful results. So, we have looked at the classification of artificial intelligence. But first, let us briefly consider the differences between machine learning and humans. So, when a person does the programming, generally speaking, there is data. A person takes that data and writes the code themselves. They do the programming. Whether using a for loop or an if statement, they say, do this, do that. When you program it, the computer uses that to solve the problem. Then an output is produced. So a person designs the algorithm and writes the code, and then the computer outputs the answer to the given problem or data. That is how human programming works. However, machine learning can be described differently as a way of programming automatically. For example, the input only requires data. Think of it as the computer, not the human, writing the program by learning from this data. In a way, it creates the model itself. Once it uses that data to build the model, that model
solves the problem and produces an output. So the machine automatically designs the algorithm.
Then it outputs a program that provides the answer to the given problem. Now, calling it a program might sound a bit awkward. So just think of it as outputting a model, a certain model. But when a person does the programming, they build the model themselves and use that model to output the answer.
Now, if we look at the difference between machine learning and deep learning, as I mentioned earlier, the most basic way to compare them is that machine learning uses neural networks, while deep learning uses deep neural networks, or DNNs. I said the only difference is that it's deep, but that's just a basic way of classifying them.
Looking at a more fundamental difference, in machine learning,
if you have input data and need to predict something like vehicle performance, you don't actually use all the complex high-dimensional data from the various systems in the car. Instead, an expert extracts the important features.
Oh, really? So things like engine size and such, then by using only those values, you create a somewhat simple model to perform classification in this case. So it classifies them and provides the answer.
Oh, the example here uses an image. So if an input image comes in, and if a person defines specific features of the image, like whether there are wheels or not, or whether there are windows, or whether it has certain features, and by collecting that data and building a model, the model then classifies it as either a car or not a car.
For example, how does deep learning do it?
If you think of this input data as an image, it is very high dimensional data. It is not just a matter of whether there are windows or wheels, but if you look at the image itself, you can think of it as pixels. And in high dimensional pixels, it is complex data containing colors and RGB values. If you just put this into deep learning, it extracts the features on its own. So it automatically passes this high dimensional large scale data through a complex network to eventually extract important features. However, these features are something highly nonlinear that are difficult for humans to interpret just by looking at them, essentially latent values. Then, based on those values, deep learning produces the final output. So, whether it is a car or not a car. So, extracting features from high-dimensional data manually to produce an output is machine learning, but in deep learning, the model extracts important features from high-dimensional data entirely on its own without any human intervention. Let's take a look at the three categories of learning. From a machine learning perspective, learning can be broadly divided into three types: supervised learning, unsupervised learning, and reinforcement learning. So, what exactly is supervised learning? Labeled data, meaning a label is the correct answer. So saying this photo is a cat or a dog is what we call a label. We train using data that has been labeled. And when we do that, what can we do?
It can mainly perform classification and regression. So what is classification?
Earlier, since the data comes with labels, such as which photo is a cat and which is a dog, the model can distinguish between them. When new data comes in, it identifies whether it is a dog or a cat. So it learns the boundary that separates photos of dogs from photos of cats. Then, what is regression? It is predicting something with continuous values. For example, weather forecasting or stock price prediction would be possible. So, if you have a data like temperature readings, you can create a straight line or a curve that fits them. This is what we call supervised learning. Since there is a correct answer, you are learning that answer.
Then what is unsupervised learning? What is unsupervised learning?
It is learning from data without labels, without any correct answers. The main purpose is usually clustering. Now, clustering looks very similar to classification, right? But what is the difference? Clustering is about dividing data that has no labels or answers. How do we divide it? We simply train the data without answers and group those with similar features together. Once grouped, the model clusters similar items together. After grouping them, we can look at the results and analyze them ourselves, realizing, oh, these are dogs and those are cats, right? So, Aisanso on the right classification is about finding the boundary that distinguishes features when we already know if it's a dog or a cat.
In a way, clustering is learning without that knowledge, grouping data based solely on their similarities, and then finding the meaning of those groups.
So, in the real world, clustering is perhaps more meaningful than classification. That is because in most cases, there is very little labeled data.
Right? And another important task in unsupervised learning is dimensionality reduction.
So, what is dimensionality reduction? We will learn the specific methodologies later, but for example, let's say you have input data. Suppose there is some high dimensional data here as input. For example, if we take photos as an example, we input the pixel values, and for instance, though this is simple, we reduce 4-dimensional data down to 2 dimensions.
Through some operations, it reduces it to 2 dimensions and then restores it back to 4 dimensions. It restores the 4 dimensions so that the original input data can be retrieved as it was. That means the data was originally represented in 4 dimensions, but it was reduced to 2 and then reconstructed. If you can reconstruct 4 dimensions from 2 and get the original values, it means the data can be sufficiently represented in 2 dimensions. So the dimensionality was reduced. What is the advantage of this?
In this 2-dimensional space, for new data, if there is some input data, let's say it becomes 3.5, 4.5 when it enters the 2-dimensional space.
Yeah, then it becomes 3.5 and 4.5. If I just input new data like 1.5 and 2.5 and reconstruct it, I can create entirely new data in 4 dimensions.
So, if you reduce it to a lower dimension, you can sample values in that low dimensional space and reconstruct them through the network on the right to create new data. You can actually create new images. So once you have dimensionality reduction, you can build generative models. And so you can create a generative model using deep learning. So you can see that dimensionality reduction also makes generative models possible. And finally, reinforcement learning. We won't be covering reinforcement learning in this course.
Now, reinforcement learning is also a key area. But if we look at how it differs from other types of learning, it involves a series of actions.
So you can think of it as a way to learn about sequential actions.
You can think of supervised and unsupervised learning as learning to make a single decision rather than learning a sequence of actions. Reinforcement learning, however, involves making decisions over a period of time. For example, games are often used to illustrate this, like playing Go or Super Mario. For example, in Super Mario, I have to jump this turn, move forward the next second, and then eat something. So I have to perform a series of actions. But how do we learn in that case? In supervised and unsupervised learning, we provide the data. But in reinforcement learning, we don't provide data. It collects data from the environment itself to learn. So, for example, like the Super Mario example earlier, it just plays the game and learns data through experience via trial and error. So it learns that moving forward leads to death, jumping here keeps it alive, and next it needs to eat something or it dies. It keeps going through trial and error, and that trial and error becomes the data.
So in reinforcement learning, there is usually an agent and an environment. The agent is Super Mario. It is the subject that learns.
The environment is the game itself. So you have to create an environment, whether it is a simulation or a real-life situation.
Then, when Super Mario takes an action, like jumping, moving forward, or moving backward, the environment provides the result, like, oh, if you do this, you die.
If this happens, your score goes up. When you provide a state, you give the agent a reward based on it. So you would give a reward like increasing the Super Mario score or gaining an extra life. Or if it dies, you would give a negative reward instead. Learning by doing this is what we call reinforcement learning.
So
Looking at the deep learning techniques that belong to these learning methods, The most commonly used one for classification is CNN. CNN stands for Convolutional Neural Network, and it is mainly used in the field of image classification. Of course, it is also used in regression analysis, but in any case, convolutional neural networks are used a lot in classification, and deep neural networks are also used frequently. So you can think of convolutional neural networks as a more advanced version of the deep neural networks I introduced earlier. Next, for regression analysis, we mainly use recurrent neural networks, or RNNs. You can think of these as deep learning models that learn from time series data. We won't be covering them in this session, but it's good to know that they are used in that way. For now, in unsupervised learning, as I mentioned earlier, we can perform dimensionality reduction. By doing that, we can create generative models. The most basic methodologies for these generative models are VAE and GAN. Also, for dimensionality reduction, there is the autoencoder or AE. Think of the AE methodology as being for dimensionality reduction, and through that you can see how VAE and GAN work, with GAN creating new data. We will learn about these later, but VAE is actually the most difficult one. So it is a model based on very probabilistic deep theory, and you can think of GAN as an idea created to produce good practical results. Now, with deep added to reinforcement learning, deep reinforcement learning using deep learning, methods like DQN, A3C, and PPO are the most widely used.
So we have looked into deep learning a little bit.
There is a problem we need to think about. I like this saying, don't just try to solve problems correctly, solve the right problems. What this means is, as I mentioned, we are applying deep learning to our designs quite a bit. Design, or what we call design in English in a broader sense, is defined as the process of defining a problem and solving it. But these days there is too much focus on solving problems. Since AI itself is so popular, the focus is on how to solve problems well. So more people than you'd think have, it's become democratized in a way. So this artificial intelligence, the programming platforms themselves are so well developed that it's easy to use libraries. So many people have started handling this easily. It will become even easier in the future, and eventually it will just become a tool. A time will come when it just becomes a simple tool. The problem is, when you go into the industry, when you go to the industrial field, people are struggling not because they cannot do artificial intelligence, but because they cannot define the problems that need to be solved with artificial intelligence. The reason is that the problems currently being solved by artificial intelligence are mostly limited in restricted areas like generating faces or natural language processing, where there is a lot of existing data, and it is a domain that computer science has worked on for a long time. It performs very well, but when you actually go to a manufacturing site without that domain knowledge, you cannot properly define the problems that AI can solve. So, if a problem is defined incorrectly, no matter how fancy the AI you bring to solve it, you won't get a meaningful answer. For example, artificial intelligence. We are currently focusing on deep learning as a field of artificial intelligence. Since deep learning is a data-driven model, it requires data as input. If the data is garbage, the output will inevitably be garbage. That is why we call it garbage in, garbage out. Therefore, people in the engineering domain must accurately define the engineering problems. And you have to precisely define which problem to solve, and then collect the data needed for that problem. At first, it will be raw data. Have it to clean up that very unrefined data using your domain knowledge. After cleaning it, you need to map the problem itself into one that AI can solve. and pre-process the data so that once it is mapped, it becomes trainable data.
Tete fusirike. That raw data, if you use AI to solve the problem with that data, it gets solved well.
So in actual manufacturing or product development site, as if you just define the problem well and have someone with domain knowledge clean and pre-process the data, even a very simple deep learning algorithm can achieve excellent performance.
Conversely, if you ignore those things and just mindlessly feed all your data into artificial intelligence without any purpose, the problem won't be solved well. So, what I would like to recommend to you is that you must have your own domain. Moving over, you cannot rely on artificial intelligence alone. You must possess a deep understanding of your own domain. At the same time, you need to understand AI. Only then can you use AI to solve problems correctly. So I have introduced what deep learning is, and I have explained that defining the problem is important.
However, our course is primarily about learning the methodologies needed for problem solving. You can apply these methodologies to your respective domains and fields of study. So, from now on, I will introduce how we can apply the deep learning we will learn to engineering design or mechanical design. So, the topic our lab is researching is ultimately how to solve the problem of enabling AI to design engineering systems on its own. We call it X plus AI. So how do we integrate AI into a domain called X? Or it is also called AI plus X. The nuance differs slightly depending on which one you choose to emphasize. Now looking at AI, as I mentioned earlier, it is a methodology to solve problems. So in a nutshell, AI, especially deep learning, is function approximation. It is approximating a certain function. If there is a system and we have an input and an output, if we call the input X and the output Y, we are ultimately approximating the function f of X. It is fitting the data. That is the role of artificial, deep learning. But now we can approximate functions using high-dimensional data and massive amounts of big data that were previously impossible to handle.
So for it, the turns out this is the roles it can play were introduced earlier. It can do predictions, generation, clustering, classification, and there are various other things it can do.
The tasks. But we look at how to apply those tasks that it excels at to X. In the field of mechanical engineering, where I primarily work, artificial intelligence is already being used quite extensively. So it is being used extensively in various fields such as robotics, autonomous driving, smart factories, healthcare, and bio. So the area we are interested in is design. In design such as optimal design or computer-aided design, engineering and manufacturing, we deal with how artificial intelligence can be applied to computer-based design and analysis technologies. That is our domain.
Now, if we look at how artificial intelligence can be applied in fields outside of general computer science, let's first examine it from the perspective of optimal design. When performing optimal design, it is generally divided into three categories: size optimization, shape optimization, and topology optimization.
So topology is called phase. So we call it phase optimization. And phase optimization is for example, with a size optimization, if we are designing a bridge, we apply constraints and forces and then determine the thickness of these components. That is what you would consider size optimization. In this case, holes are made in the bridge, and you can think of it as optimizing the shapes to better withstand force. Now, topology optimization means giving the entire design space from the start to decide whether to add or remove material to create an entirely new topology. To put it simply, topology means designing from scratch, including the number and location of holes. So, for shape optimization, if we define a situation with 6 holes, for example, and determine their shape, in this case, we leave everything from the number of holes to their size entirely up to the computer. When we say we can design like this, why is deep learning used so much for topology optimization? To explain topology optimization in more detail, it was initially used a lot in structural design, utilizing theories learned in solid mechanics. So there are boundary conditions like this. For example, the object must be constrained on the left side. If it is constrained so it cannot move left or right, and then you apply force here, the object will deform. But we first define a rectangular design space, and once that is set, we divide it into a grid. We have divided it into a grid like this. We divide the grid like this and decide how much material to put in each element based on its position. So if we decide on the density of the material, a solid black color means the space is completely filled with material. And if it becomes 1, and if it becomes 0, it means we will not put any material in at all. If it is 0, it means we put in that much. Ultimately, this allows it to withstand the force, or in engineering terms, it maximizes stiffness. In other words, it prevents deformation under a certain force. Conversely, this is minimizing compliance, since compliance and stiffness are opposite. So, we are finding the material density that can minimize compliance. Naturally, the best option would be to fill it completely. Filling it completely is the best.
Then it would cost a lot in materials. So we remove the material little by little.
Gradually remove material, and while removing it, we might be told to reduce it to a specific volume, say 1/2. For example, if we are told to reduce the total volume by half, we then find the optimal shape by determining where to place the material to fill that 1/2. This is topology optimization. I gave you a long introduction, but it is a method originally used in engineering design. Looking at it, it actually looks like pixels in an image. Determining the density of each element is similar to selecting the red, green, and blue values for pixels in a photograph. So, thinking that we could treat this like an image, we are now using deep learning for it extensively. So, it's interesting to see that Google has been releasing various studies on deep learning, but was it the year before last? Google published a paper on this topology optimization. It was quite fascinating to those of us in the field when we looked at it. Why did Google use deep learning for this topology optimization? Why did they explore this field?
It seemed like a field Google would have no interest in. But when I looked at the author, it was this person.
I visited this person's blog. Looking at their background, they have a doctorate in physics. They aren't from computer science, but a physics PhD. And they introduced themselves as a physicist, a data scientist, and a software engineer. Then they joined Google. After joining postdoctorate, so looking at this is actually his own domain. He is saying that he has a domain in physics, plus he is a data scientist and a software engineer. So I realized that from now on, the domain is definitely becoming important. So if this person hadn't known about physics, they wouldn't have been able to approach this problem at all, because without that domain knowledge, they couldn't have defined the topology optimization problem in a way that artificial intelligence could solve, right? But because this person was able to define it, they were able to propose a new method using deep learning.
So while existing researchers have already been doing a lot of topology optimization, we can see that by using deep learning, the diversity of domains is expanding significantly, even reaching companies like Google, including in engineering design.
So, a little more on how deep learning can be applied to engineering design.
If we look at it, simulation-based optimal design is being used quite a lot. When it comes to simulation-based optimal design, if you have unlimited time and money, the best way to design something is to just build it yourself.
You could build everything yourself and test thousands of different cases to see which design performs best. But that is realistically impossible. So we use simulation-based design optimization. But how do we do it?
For example, to give you an illustration, I once designed a truck suspension for Hyundai Motor Company. To optimize it, if you want to perform an optimal design for the springs of a large truck, you first need to define the problem. Where exactly are you going to design?
The system itself is high-dimensional data. Since it is a three-dimensional object, you cannot optimize every shape or every dimension all at once.
So we perform parameterization like this. When you look at it from the side, you can define the height, the length here, the length there, and the angle.
Since we cannot optimize everything, we usually fix the unimportant parts and select only a few specific areas we consider important as variables. We then optimize only those parts and keep the rest fixed.
After that, so usually when doing optimal design, three things are needed to define the problem. So an objective is required. Objective function. 소번 거처럼 가하 뭐닝을 넘버하네디. What are we doing? For example, maximizing stiffness, then what are the variables? What are the design variables? Like what are we optimizing and what are the constraints?
Deformation must not exceed a certain point, or the stress in a specific section must not exceed a certain limit.
Would set constraints like that. After that, you can vary these variable values, perhaps by setting boundaries like between 0.1 and 0.5 or 7 and 8. By fluctuating within those ranges, you can create new design values. Then you run simulations on those values.
We simulate the engineering performance for that, which is usually called computer-aided engineering or CAE analysis. We use software to perform the analysis and then we stack up the results.
So when the design, the X value is input, we run a computer-aided engineering analysis to collect the Y value or performance value, which then becomes our data. We then use that data to create an approximation model.
We call this approximation model a meta model or a surrogate model. After creating such a model, you can think of it as the shape of the model. You create it as a function, and once that function is built, you perform the optimization. So for optimization, we would use an optimizer. For example, if we use a gradient-based method to maximize stiffness, it will gradually find the point of maximum stiffness. This is simulation-based design optimization, but how is deep learning used here? First, as I mentioned earlier, one of the major strengths of deep learning is its ability to perform dimensionality reduction. So, while we previously used rule-based methods where experts relied on their domain knowledge to make selections, we now take this high-dimensional data and reduce it to a lower dimension instead. We just reduce it to a certain number of dimensions, like 64, and then optimize all those values in that reduced state. Originally, it was too high dimensional to optimize everything, but by reducing it to a lower dimension, we can find the best design within that space. You can perform optimal design very effectively, and since you're reducing it like this, it naturally becomes a parameterization. This means we can now represent the entire design using parameters, and that gives us the advantage of being able to perform optimization within that reduced space. Next, in the process of creating simulations and meta models, what can deep learning do? It can perform data generation. As I mentioned earlier, once the dimensions are reduced, you can create new data. Since we can generate new data, instead of just changing a few design variables to create new designs as before, we should be able to represent a truly diverse range of spring shapes. So those things, if there is a vast amount of CAD data,
for that design in the actual industry, it is very convenient. But when you go into the actual industry, there is not that much. Especially even if you go to a large company, there are not many cases where they have that much data. So as much as can be used for deep learning. So for us to use deep learning in an industrial setting, the bottleneck is that we have to regenerate data to perform any kind of training. So deep learning can be utilized for such data generation. And then regarding the strength of deep learning, which is its predictive capability, the existing meta models were essentially just functions, and we have been using machine learning for that in the past.
We have been using machine learning, but with deep learning, we can now predict even higher dimensional data and highly nonlinear engineering performance much better.
And finally, we move on to optimization. What do we use to solve the problem? There is something called inverse design. So what is inverse design in deep learning? It is reverse engineering. So normally prediction means you input the design or X and it predicts the performance. Inverse design is the opposite. You input the performance and it gives you the design values. So if you provide a target performance, for example, telling the deep learning model to achieve a certain stiffness, it immediately tells you this is 0 C. This is the design that will give you that. In the past, we had to check the Y values to find the X, but now we can find the X all at once in a single shot. Next, we use reinforcement learning as the process of finding these design values is somewhat sequential. We treat these sequential steps as reinforcement learning to find the solution.
We can utilize it. So I have introduced how deep learning can be used for simulation-based optimal design.
To elaborate further, if we look at the similarities and differences between the meta model mentioned earlier and deep neural networks, a meta model essentially collects engineering data, such as experimental or simulation data, and uses machine learning to approximate functions. Ultimately, the goal is the same as deep learning. It is the same goal. You are approximating a true function based on certain data. So from this perspective, they are the same, but what is the difference?
For more classical machine learning techniques, we often use what is called mean squared error, which will be introduced later. So we mostly use methods that train by minimizing the difference between the model's predicted value and the actual true value.
Now, for deep neural networks, they fundamentally deal a lot with probability. So I think we can look at it more from a maximum likelihood perspective. We will cover this later as well. So if you look at the problem from a probabilistic perspective and formulate it, it actually ends up being the same as the mean squared error. If you assume a certain distribution, which we will also learn about in detail later, then in the end, if we look at the differences,
the difference is that it deals with probabilities a bit more. And ultimately, while machine learning meta models can only handle very low dimensional design variables, deep learning can handle very high dimensional data.
But since it can handle high dimensional data, the number of design variables isn't limited. But what's the problem? You need a large amount of data. And as we will learn later, backpropagation must be possible. You can only use deep learning if these conditions are met. And if that happens, it becomes very powerful and generalizable. So it can learn with some generalization, even if the conditions change slightly.
Yes, now let's look at the difference between optimal design and reinforcement learning. A feature of optimal design is that there is no training process, so there is no need for experience in searching for a solution.
And the optimization just provides the optimal solution for each case, so when a new optimization problem comes in, it needs time. In other words, it has to be solved all over again. That is why it requires a lot of time during testing.
But reinforcement learning is about continuously training on how to find a solution that is right based on the data.
So, while it takes a lot of time at the beginning, when a new problem comes in later, it doesn't optimize to find a solution but predicts it immediately. So there is no time required during testing.
right? So with optimal design, if you give it a new problem, it has to solve it again. But with reinforcement learning, if you give it a new problem, it doesn't solve it. It just predicts the answer right away. And for optimal design, all the requirements used in existing engineering design must be fixed. But
In the case of reinforcement learning, even if those requirements change, it adapts to the situation and provides a generalized answer.
For example, think of optimal design as solving a maze. Given one maze, it will find the optimal path every single time. But in the case of reinforcement learning, it has already learned a variety of mazes. For example, even if you give it a brand new maze it has never seen, it finds the answer right away. And optimal design is mainly used for single decisions, meaning it is not for time series or sequential data, but rather for making a one-time decision. Because design doesn't change as time goes by, for example, but reinforcement learning is mainly used for sequential decisions, right? You do this now, then you do that next, and then you do this other thing. So it's used for sequential decisions. So to put it a bit more, optimal design is like catching a fish for you every time, while reinforcement learning teaches you how to fish. That is the difference.
I've given you an introduction. Since optimal design and optimization are essentially the same as what we call optimization in deep learning, understanding their similarities and differences will make it easier to organize the problems as they share the same fundamental theory. So looking at the big picture of where deep learning is being used in engineering design, it is used extensively in topology optimization, which I introduced earlier. And then there are many studies on optimal design using reinforcement learning and inverse design, as I mentioned earlier, predicting an optimized design immediately when target performance is given. And it is used a lot in material design. So material design, it is used a lot in areas like nanophotonics. Also for CAE and simulations, CAE refers to fields that use computers for analysis. Since those simulations take a very long time, deep learning is often used as a technology to shorten that time or to make predictions directly. Next, since we have a lot of CAD data, we are conducting research that utilizes that CAD data, research that connects to manufacturing to assess manufacturability and shape parameterization.
So, research on parameterization and dimensionality reduction for complex three-dimensional shapes, as well as research on predicting customer preferences to see if these designs will succeed in the market, is being actively conducted. And another area we are very interested in is generative design. Generative design is a term that has been used for a long time, so it is a very broad concept that refers to technologies that can automatically digitize and explore designs. In modern terms, you could say it is a technology where artificial intelligence creates various designs on its own. However, to use this technology, you can utilize all the technologies in these areas. So, this can be seen as a core technology for how artificial intelligence will design products in the future. If you take a quick look at this video, it's designing a chair on its own. This is actually generative design using topology optimization. So, the computer designs various options on its own, and you just have to select the one you want. So we can check the performance, make engineering comparisons, and things like that. In the past, these technologies mainly utilize mechanical engineering techniques, but now, by combining them with data-driven deep learning, they can perform various roles and enable automation. So, and also what is generative design? To explain it simply, there are various methods for generative design. So, among those, if I introduce generative design using topology optimization, creates the stiffest, most rigid structure under given load and boundary conditions. But when creating this, you can consider many things. There isn't just one single design. While optimization might have a global optimum or a best solution, there are various local optima that exist, and you can find those various local optima as well.
The second point is, well, this optimization design problem isn't solved with just one objective, but rather with what we call multi-objective.
So there could be multiple objective functions.
For example, in engineering, there are various load cases, such as this load condition or that one. You might need to satisfy all those cases, or perhaps the design must withstand force while also being manufacturable and aesthetically pleasing. Since there are many such objectives, there are many designs that can satisfy them.
So, there's what we call a Pareto front, where there is no single design that maximizes every objective, but rather they involve trade-offs. If it is aesthetic, it might be less functional, and if it is functional, it might be less aesthetic, meaning there are various designs that exist in between.
So the third and finally, there are various design parameters involved in this optimality or topology optimization. The values change depending on how a person defines those parameters. That is the optimal design values. So by combining various design conditions, for example, different problems are created and various designs are produced accordingly.
There is generative design using topology optimization. However, that generative design in the past did not actually utilize data.
But with the recent emergence of deep learning, as you can see, we used hundreds of thousands of images we received from GM during our doctoral studies to train a model using the VAE methodology you will learn about later. And by training it this way, it generates these entirely new shapes.
And once you train it, you can compress it into a lower dimension and represent it in that space. So in that low dimension, for example, if you pick a point in 2 dimensions, a coupe appears. But if you move to the right, it transforms into an SUV.
Picking another point resulted in a truck, and moving along from there resulted in a convertible. So these high-dimensional vehicle shapes can be densely represented in this low-dimensional space. Therefore, if you pick any point here, it becomes a new design.
So in the end, this generative model in deep learning creates a model distribution that best approximates the probability distribution of the data. So by learning this blue, we make this yellow as close as possible to the blue.
Then that yellow color is the model we have trained. Since this model can perfectly mimic the data, if we pick any point from this distribution, just like picking this one here, a new design is created. So you might wonder how we can apply this method to existing generative design.
That is how we arrived at artificial intelligence-based generative design. We will introduce applications for artificial intelligence and engineering design at the very end. We will cover that in detail then, but for example, if you have past design data, artificial intelligence-based CAD creates new designs like this.
So in the design generation phase, an AI-based CAE, a computer-aided engineering analysis tool, evaluates the engineering performance of the various designs generated.
It can evaluate whether a design is engineering-wise superior or has good manufacturability and then filter them. Once the existing designs are filtered, an AI-based human-computer interaction, or HCI, learns the customer's preference data to recommend designs that the customer might like.
It then recommends by saying, oh, this person will like this wheel design, or this design, this target design has a high chance of success in my target market.
This research becomes possible in 3 stages: design generation, design evaluation, and design recommendation. You can visit our webpage to find more papers and materials.
And I will briefly introduce an example of applying this technology to Hyundai Motor Company. It will be introduced in more detail later.
For example,
Car companies usually have CAD and CAE processes. We apply deep learning to their wheel design process. For instance, we create a two-dimensional design and use artificial intelligence to reduce its dimensions as it is high dimensional. Then, in that reduced dimension, we perform sampling called DOE. We then conduct the test.
We sample data to predict engineering performance, combine them to create a three-dimensional design, and everything is automated. After that, we automate the analysis as well. We then accumulate the data, gather engineering performance data, and train it with deep learning so that when a design is input, its engineering performance can be predicted immediately.
It performs in just 1 second the many tasks that the person used to do manually. Then, to help engineers understand the results, a lot of explainable artificial intelligence technology has been developed these days. So, we use that technology to verify what kind of engineering knowledge it has learned.
That way, it will become a reliable tool.
I have given a long introduction, so I will conclude it here. Thank you.